Hi, everybody. I'm Peter Morgan. So I represent a company called Deep Learning Partnership, which is an AI consulting company. So it's plain old deep learning for my bread and butter. But today I'm going to talk outside of that into what I see as the future. So here's a little booklet I wrote for O'Reilly. It's free to download, so go ahead. Machine learning is changing the rules. There's my company website, there's my Twitter handle. I tweet on sort of what I'm going to be talking about today a lot, so you can sort of keep up to date if you so desire. So what am I going to talk about? So what is intelligence? A good place to start, right? If we're trying to solve it, we need to ask what it is, figure out exactly what it is we're trying to solve. So I'll start by outlining what I think intelligence is. Okay, I'll answer that question today. And then we'll look at, physical systems, biological, non-biological. So the non-biological ones being computers, silicon, that type of thing. Biological systems being us, right? We are the, we are what we are trying to model. Okay, this is it. We're trying to model the human brain. And not only the human brain, but how biology does intelligence. How biology does intelligence. Okay, that's the aim of my talk, is to describe that and a system that might actually build it. And then we'll do a very quick recap on deep learning, because I've just tried to convey that biology isn't actually deep learning at all, and a lot of the talks today, particularly the neuroscience talk I saw earlier before lunch, made that very clear. Deep learning won't get us to intelligence, right? And I'll explain exactly why. Well, basically, it's statistical, and what we want is a physical theory of intelligence, right? So I'll go more into the physics and the neuroscience. Finally, we'll have a look at a theory of AGI, and I'll talk about that. So that's the very end of the talk. Okay. So without further ado, hopefully the clicker will work. So why do we want to build AGI? Well, we want to solve intelligence, we want to understand intelligence, so we want to build systems that, we can use to do all these tasks and then make money from that, or just do all the, automate all the boring stuff. And ultimately, if it's general intelligence, we can automate everything. So then we got to ask, philosophically, what do we do, right, if we build these systems? And my answer to that is we'll just get back to being more human, right? We won't have to work in factories and production lines, and even though a lot of people have convinced themselves, this is what the true meaning of life is. I don't buy it. So once we build it, it'll become more obvious what we'll have to do with ourselves. Okay, nothing to get too worried about. Okay, I'm not a doomsayer. I'm not here to say, oh my God, the world's ending. But the conversation at some point always goes there. So I thought I'd just get that out the way at the beginning. Right? So let's focus on trying to build it for the rest of the talk. So what is general intelligence? Are any of these general intelligence? AlphaGo, AlphaStar, playing StarCraft from DeepMind. I've come over from London where DeepMind are based, the Google company. Deep Blue from IBM back in the late 90s, IBM Watson, winning at Jeopardy, natural language processing. None of those are even close to general intelligence. They do very specific things. They're completely dumb. They're completely stupid. They use statistical methods, so no, they're super clever. It's like they can totally outperform us, just like a calculator outperforms us with multiplication, right? So not dismissing it entirely, but it's not general intelligence. That's not what I'm here to talk about. That's what DeepMind does. It's not what I'm trying to do. Although ultimately they do want to do that, and they've said that very, very, very clearly. But right now they're not doing it. So what is intelligence? Well, here's the answer. It's not one thing, it's many things. So it's basically we are agents in our environment, so it's our adaptation to our environment. If we were living in a different universe with different laws of physics, so gravity goes up instead of down, we would be adapted to that. And so that would be, our intelligence would be adapted to that environment, okay? So it's simply adapting to our environment, exploiting our environment, modeling our environment, and successfully predicting what's going to happen next in our environment. If you think about it, it just kind of boils down, deflate everything right now. It just kind of boils down to that, whether we're trying to win the lottery or build a rocket to the moon or even build general intelligence. We're just trying to model our environment. It just so happens that we're trying to model our brain, okay, with general intelligence. So we've done a pretty good job. We've done, the laws of physics. We've had Newton. We've had Einstein, we've had Feynman, we've had some super clever computer scientists, biologists, neuroscientists, but it's all the same thing. We're just trying to model our environment, okay? So it's not just Einstein. That's not the only thing that has to do with intelligence. It's spatially, we have athletes, that are way better than Einstein at doing the high jump, right? So he was crap at that, but very good at modeling general relativity. But when it came to hurling himself over a high bar at 7 feet, he would just fail miserably. When the high jumper goes to solve, to understand the universe right down mathematically, he would fail. So there's not one type of intelligence, okay? There's many. And that's what the G in AGI stands for. It's general. Okay, so we're trying to build things that are spatially intelligent, aware of their environment. We're not doing a very good job there, are we, with climate change and everything like that, Donald Trump, blah, 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 right? So, that's for me is a big part of intelligence, is to understanding our environment, not destroying our environment, but, kind of living in harmony. That might be a definition of naturalist intelligence, not getting too political, but, that's what I believe. Musical, Mozart, Beethoven, the Beatles, whatever type of music you like. And I've managed to turn that off. That is a type musical intelligence. Not everyone can write a beautiful melody or a symphony, but some people can, right? So these are all different types of intelligence. Linguistic, Shakespeare, or who can write a great poem, etc., etc. Interpersonal, people relationships, how we relate to one another. Social intelligence, emotional intelligence. Introspection, how we understand ourselves, how we react in society, how we go about, our place in the world, and then you build it up hierarchically into nations. Do we go to war? Do we not? I mean, how do we keep peace internationally? These are all different types of intelligence that these machines will have to do if they're truly general intelligence, okay? So it's not just building the Einstein. You can see that now. It's everything. It's physical, it's political, it's social, it's emotional, okay? A big ask, but we do that in 3 pounds in our skull, right? So biology has done it using 100 billion neurons, roughly. Somebody said 86 billion, but it's of that order of magnitude. And perhaps it's the connections, 1,000 to 10,000 synapses per neuron. So it's a very complex system. So it's no wonder, we can't give ourselves too hard a time that we haven't built it yet, because, it's complex. And also, the Earth's 4 billion years old. We've had a few years, okay? We didn't just come up with this stuff yesterday. We can go back 10,000 years, 20,000 years. We were pretty much living in caves, right? It's only the last 100 or so years that we've kind of, hit this exponential where we're taking off and the singularity is near and all that kind of stuff, right? So we're living in very interesting times. But this is where intelligence has brought us. And this is where we are. We're sitting in this conference talking about it, right? We wouldn't have been doing this maybe even 10 years ago. Okay, so we're ready to build it. How far have we come? I would argue not very far. All these talks we've seen today have all been about deep learning and statistical methods. The best we've done, I think, is around 50% for logical, mathematical, linguistic. The last talk was on BERT. It's super impressive stuff. There's GPT-2 with OpenAI. There's BERT with Google, Facebook, Microsoft, everyone. All the big tech companies are plowing ahead with these statistical methods, but they're nothing to do with general intelligence. So, statistics will only get us so far, right? And in fact, when it comes to introspection, thinking about the universe, they're actually zero. They're not even off the ground, okay? They haven't even started, haven't even begun, and they never will do because it's statistics won't do it. Physics will, statistics won't. I'm not trying to discredit anyone here. I'm just trying to focus on general intelligence, okay? Okay, so how will we get there? Well, it takes a village to create an AGI, just as it takes a village to raise a child, right? It's going to take a village to build these things. So it's not just physicists, it's not just computer scientists, it's not just, psychologists, it's all of us together. So it's neuroscientists, psychologists, physicists, computer scientists, everybody, politicians. Because this is general intelligence, we need everybody in the room together. Okay, so so physically, biologically and non-biologically, let's take a look at, how physically intelligence manifests. Okay, so biology, very clever. We start with bacteria, no central nervous system, no neurons, nothing, and yet they survive, they reproduce. They're intelligent, okay? Maybe more intelligent than us. Maybe they'll survive longer than us. The rate we're going, I'm not putting my bets right now. So, that is intelligence without even a single neuron anywhere to be seen. So they're using chemical gradients. They're just using the laws of physics to wiggle and wobble about, but they've learned how to reproduce, create DNA and reproduce. They haven't learned anything, right? That's anthropomorphism. This is what the laws of physics can do and has done, in terms of biology. The first thing with the central nervous system is the C. elegans. I think it has 130 odd neurons. So arguably, this is the dumbest thing with the central nervous system. But yet it can, understand, it can survive, it eats, it reproduces. The bumblebee has about 1 million neurons. This is how biology does things. It can navigate, it does its wiggle dance, it's societal, it lives in a society, and right up to us, the brain, the human brain, in fact, you've got all the mammal, elephants, fish, chimpanzees, us, right? So there's a whole spectrum here of intelligence. Assumably we'll start with the simplest systems and build up. But is there something here that unites these all of these systems here? Because I'm interested in understanding theoretically what intelligence is. In other words, writing down the mathematical equations that we will use to guide us when we build these things. Okay, not just sort of trying, does this work? Does this work? I'll add another neuron, another layer to my deep neural network. I want to understand the basic the physics of intelligence, or we do as a community. The AGI community. Okay, so the first thing we notice is that biology is hierarchical. We start off with atoms. They're certainly not intelligent. Molecules, neurons, they're not intelligent unto themselves, but when you start connecting these things together, the connectome, then intelligence emerges from there. And then we have us, agents, and then we have societies and nations, and finally the world. So, the whole thing is hierarchical from atoms up to nations. So this general theory will have to explain the whole lot, okay? So it's a big ask, right? We're actually trying to describe the whole thing and not just bits of it, okay? So just to kind of sort of expand your mind, put it all in perspective. So we're coming up with a truly general theory of intelligence. And that's what a neuron looks like. It's super complex. Do we need to go to this level? There's a lot of open questions. We don't know. We'll see, okay? We'll just see. Nature does, clearly, because that's what a neuron looks like. But when we build these systems, will we have to? It's a very, very, very interesting and open question right now. Okay. But it won't stop us, perhaps, coming up with the underlying theory. So this is what the brain looks like. This is what intelligence looks like. It's organized into structures, repeating structures of about 2 million neurons in these so-called cortical columns, again and over and over and over again. So if somebody goes blind, God forbid, that some of those neurons that we use to process visual information are quickly repurposed into processing sound. Okay, so there's a generality there. These are just information processing systems that seem to have some sort of generality. So we do know that. That's something we do know so far. And I'm going up the hierarchy here. Here's the connectome, so it's all connected. Besides these tens thousands of synapses between each neuron, these things are organized into some larger. If you go up one level in this hierarchy, then you start to see this connectome forming, whether that's in humans or even bees. There's this layer above the neurons that maybe that's the right layer to start with. Okay. And then above that, then that's attached to a central nervous system, and all living beings, a fish, a bee, a human. So it's not just a brain in a jar. Although some might argue Stephen Hawking was kind of that because he had that terrible disease, and there are people. So we can function like that, but we're really interested in building the whole physical as well. But the brain is the main thing. Once we've cracked that, we've cracked intelligence. But I'm just saying, we connect it to the rest of our system. Do we need kidneys? I doubt it. I doubt we'll have this thing, a system with kidneys and lungs and everything else, right? But that's how biology has done it in every single thing. So there's this other part, 90%, which I think we need to worry about the brain more than the rest of it. But the rest of it's super clever, but kind of clunky. It's just nature's put us together like that. We may not need to go down to that, consider that so much. But if we're building robotics, we will. But a robot might not have kidneys, but it'll have, it needs to be able to move around fluidly, and we haven't quite got there yet. Even though Atlas, it does nice backflips and it's getting pretty good, isn't it? Every month, Boston Dynamics comes out with a new video. It's like, oh my God, it's like so human, and then they beat themselves. But it's not intelligent. It can't play chess. It can't, ponder the universe, its own existence. It doesn't even know it's alive. That's how dumb it is. But it's very good with the physical part. Okay, so it's all part of intelligence. And then the social systems. We talk about cloud robotics, swarm robotics, social intelligence. That's the final layer. Okay, so. Here's where we are with the non-biological. We've started off with CPUs, the von Neumann architecture we've heard about today, separating the processing from the memory. And then we've also heard that biology doesn't do that. It does the processing and the memory on the same thing. A neuron is both a memory and a processor. So none of these, this is all von Neumann architecture, okay? So that's what it looks like. It's beautiful. We saw a picture of a TPU version 3 in the last slide. It's like a supercomputer. It does like a petaflop or something or more. Graph core, there's 100 petaflops in like 8 racks. That's the world's most powerful supercomputer. Almost, not quite, but it's getting up there. So these are ASICs. They're specifically designed to multiply huge matrices, billion by billion matrices together, which the brain isn't doing clearly. And, that's how many times bigger than the brain is that, right? It's got nothing to do with general intelligence, but it's super good at multiplying. It's good at linear algebra. It'll statistically, calculate things. That's why BERT will get statistically brilliant, but it'll never understand Shakespeare because it can't, because it's linear algebra, right? Linear algebra doesn't do that. Okay, and there is the world's biggest. It's 3 exaflop at Summit, chock full of GPUs and I think AMD processors. Super impressive. But it's as dumb as a brick, right? It doesn't do anything. It's a big calculator. So what are we missing? So we do all that in 3 pounds. Right? We don't need three football fields or 10 megawatts. We need a couple of sandwiches, an apple, and a drink, and we can discover the laws of the universe. Okay, so clearly we're not even close by any of those other approaches. Maybe one approach in hardware is neuromorphic computing, which stated aim is to replicate the brain, okay, in hardware. And so there's a project called Spinnaker, part of the Human Brain Project, which is doing that. Steve Ferber, who was part of ARM, based at the University of Manchester, been working for the last 20 years. He's the team there have built, now under the wing of the Human Brain Project, have built, I think, 1 billion artificial neurons. So they're analog. They process the information using analog, not digital. And it's not the von Neumann, it's kind of combined. So they call that memristors, where the memory and the processing is combined in the same place. And the architecture looks completely different. There it is. That's a billion neurons right there. So immediately we see, it's a little bit smaller than the others. That's all analog computing. And that's what it looks like. So we start off with 1,000 neurons per core. And then we put them into chips, and it's hierarchical. Then we put 48 chips in a board, 24 boards in a rack, and we have 10 racks. Right? And that's sitting in a data center in Manchester today. And you can log in now if you want to, set up an account, log in and start processing stuff using neuromorphic computing. And you can put in the MNIST data set, you can play Sudoku, you can play chess. And it doesn't do deep learning at all. It's processing it with neuromorphic algorithms and hardware. Okay, so for me, this is definitely a step in the right direction. So hardware is important. It's not everything. Obviously, the algorithms need to be there as well. But I think we need to be running it on the right hardware. Otherwise, it's a simulation. You can always simulate anything on a chip, but you need, they've done that in the Human Brain Project using, the von Neumann architecture. I think they processed a second of what the brain can do. It took them like a week in the whole data center. So, you can always simulate things, but it's not efficient. So you can actually simulate in real time using this neuromorphic architecture because it runs efficiently like the brain. I think it's about 1,000 times less efficient than biology, whereas the CPUs and everything else that we saw digital is about 1 million times less efficient. So it's definitely a step. And this is the first generation. So we're going to iterate just like we did with the CPU processing and the digital. We've had 50 years. We've got 10 billion transistors on a thing a centimeter big, right? So we'll do the same with neuromorphic. We'll have generation upon generation. And soon we'll have 100 billion neurons because it's Moore's law. It's exponential. And we will see sort of human-level intelligence. Whether it will be sentient and is down to the algorithms, actually. So I think we have the hardware. We're at the very beginning of this journey with the hardware, but we need algorithms. So let's look at the algorithms. So that's another one, the brain scales. That's the University of Heidelberg here in Germany. That's a part of the Human Brain Project as a spinnaker versus the Google TPUs. I would argue the one on the left with neuromorphic is the right hardware to be working on for general intelligence. Okay, and there's quantum computing, nothing to do with how the brain works, but sexy pictures, so I put it up there. And it is like the last form of computing, right? You cannot forget it. It's a big deal. It's going to come online, but I don't think it will be, used to, understand nature too well. I think biology doesn't use it, so I doubt we won't have to go to the quantum level, but the quantum will be very important in other aspects, perhaps not general intelligence. Okay, so there's the summary of everything I've talked about, the 4 different types of hardware, the digital, the neuromorphic, quantum, and then the biology, right? So we want to try to build the thing in the lower right-hand corner here. And I think neuromorphic is getting, that's the way we'll do it. And that's what they look like, okay? So the brain, you see the similarity a little bit. The neurons in the brain, the digital, the neuromorphic, and quantum looks a bit out on its own weird, but ultimately it's these little units of information processing. Okay, and then the data center of the future won't just be classical computing, it'll be a mix of quantum, neuromorphic, and classical. So deep learning, quick recap, that's what it looks like. This is what general intelligence isn't. So it's not that, and that's, deep learning is not AGI. So AGI is linear algebra. So, you're just summing up the weights times these vectors and billion by billion matrices. It does not give us a neuron. Absolutely, not even close. It never will do. And it was never meant to be honest. If you talk to the researchers like Jan LeCun and Jeff Hinton, we're not trying to imitate the brain at all. We just found the stuff that works really well. And then Jeff Hinton, he's in my last slide, says that, if we think really hard about how nature does it, biology, that's how we're going to do it. And he's recently said, everything I've ever done on deep learning is sort of, I'm going to have to put that to one side now, because to get to the next level, and I saw a slide in some other presentation today, it's starting to get a bit mainstream now. Deep learning is running out of steam. We can maybe tweak the knobs and get another 2 or 3%. of accuracy, but yeah, where do we go? It's not general, it's very specific. It's not going to give us those 9 types of intelligence, and I think that's what people are trying to say, even though they don't quite realize perhaps what they're saying. But that thing on the left is what we're trying to build, not that little bit of linear algebra on the right. Okay, so what is the theory? Okay, I could just walk off the stage now and say, I don't know. Thanks for coming, spending all your money, but I'll try, give you something, a bit more than that. So let's see. So I mentioned earlier that it's not statistical, right? So what is it? It's physics, right? Everything is built using the laws of physics, so why not the brain, right? Why not? Let's start there. It's nice and simple. So what do we know about physics, right? Well, we know Newton's laws, we know relativity, we know general relativity, we have Maxwell's equations from last century. We're standing on shoulders of so many giants here, Maxwell, Newton, all the greats, Helmholtz, Boltzmann, Gibbs, we got the laws of thermodynamics. We got quantum mechanics. We don't think we'll need that, but we still have it. We have relativistic quantum mechanics. We have stuff we don't know, dark energy, dark matter. We are probably not involved with intelligence. The thing is that all of that can be encapsulated in something called the principle of least action, which says that nature behaves to minimize the free energy of any system, whether that's microscopic or macroscopic, whether it's a millisecond, a nanosecond, or the age of the universe. There's this fundamental underlying principle of physics. If you did a PhD in physics, who did a PhD in physics? Yes. So a couple of people here will have seen this principle of least action. And you write it down, and it's a nice, beautiful formulation. You can write it down in Lagrangian or Hamiltonian form, but it's, one line, and you can use it in principle to describe any system, okay? I say in principle because, nature is complicated. The brain's complicated. As soon as you get more than a few atoms, or a few molecules, it's hard, right? So, but in principle, this is the underlying principle. So that's where I'm going to start, right, with the theory of intelligence. I'm going to say if we can use it for everything else, then let's apply it to the brain. See how far we get. That's what it looks like. There's a beautiful book just written, I think, last year at Cambridge University Press. Surprised me there was nothing else before this because it's been around about 100 years. It's called The Principle of Least Action. It's got all the different examples in the world of thermodynamics, classical mechanics, steam trains, computers, digital, quantum, everything. Chapter on each, how it's applied, how it's applied, how it's applied, how it's applied. So they need an extra chapter on how it's applied to the brain, I think. But that's what it looks like. That S is the action, the Q is momentum, the T is time, and Q dots, the dV, dt, the change of momentum with change in time. And delta S equals 0 is all of physics. It's the change in action. Nature acts so that delta S, where S is the action, it tries to minimize that quantity where S is that in terms of a Lagrangian. Okay, don't worry about the math or the physics. We're not going to go there. But so let's apply that to the intelligence and see how far we get, because it works for everything else. Okay, so again, it's not just about pattern recognition. It's about modeling the world. Okay, we model stuff. We can imagine. We can problem solve. We can build new models. We can understand, right? We don't just do statistical analysis. Otherwise, it'd be zombies, right? Or we'd be a silicon chip. We'd be built in an Intel factory, and we're not. So here are some theoretical approaches. I'm going to choose the Friston active inference one, which uses the delta S equals 0. The others don't, but these are very, 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 credible attempts at general intelligence. And all of these people have been working at least 30 years on these theories, so they're certainly not to be dismissed, and let's pick this one and just all the others are wrong. There's going to be bits of each that kind of have some, there's going to be overlap. So, Helmholtz started with statistical physics, right? The brain is 100 billion neurons. It's a big, messy, warm, complex system. So statistical physics is over 100 years old.
I don't want to rush you, but I said you have 30 minutes here.
How long?
I'm going to be for democracy, and our next speaker is already...
Oh, okay. So I will wind it up. Yeah, let me wind it up. So, 30 years for all of these, right? I'm going to pick Friston in the last 2 minutes. Okay. Now, active inference, we can look this up. Again, it uses the free energy. It's minimizing the free energy. Let me just flick through and then I'll sum it up. There's Professor Friston there, and we don't have time to hear him. So this is what it looks like. We can draw diagrams and pretty pictures. We can write down equations. We can have us and the environment acting back on the agent acting back on the environment. All the physics is in place. We can write down the equations for it. We can do it for bacteria or the brain. So it works on all systems. There's the math. It's super, super ugly, but that's theoretical neuroscience. And that's the equation that's like the general theory of relativity for the brain, right? So there you saw it. He's got loads of papers. Can we build it? I say yes. We have the data, we have the theory, we have the algorithms, and we have the hardware, okay? And there's some AGI project. There's Marek's here, Ben's here. There's Jürgen Schmidhuber's not here. These are all super clever people doing super clever things. And I picked out active inference as one because I feel it's the one most based on physics. And I'd say we're at the beginning of our journey. It might take us 5 or 10 years to sort of build us as we wait for the hardware, especially to mature. I believe we have the algorithms. It's a super bold statement to be saying, but I encourage you to read some of the papers. And there's Jeff Hinton saying at the very end, this is 3 years ago, the conceptual breakthroughs will take us. We need new conceptual breakthroughs. I believe the breakthroughs are going to come when we understand the brain. Thank you very much.
I'm so sorry for being so rushed. I also would like to know more. Marek, can I steal 5 minutes of the Q&A? So for just one question, I know that he's going to make it up to you.
Okay, one question.
He owes you 5 minutes of lifetime, yeah? I'll make sure you get that.
I do.
5 minutes of your lifetime to him.
Thank you so much.
Yeah.
Okay. Thank you so much for the question. Sorry for your time, and taking one question. So I'm just going to be very quick to keep on schedule. So I'm going to just speak in very short words. So Richard Feynman, you've been a music producer besides all your other work in the academia. And you've shown us a great slide where you said for AGI we need computer sciences, physics, neurosciences, and psychology.
Yeah.
So bringing these 4 things together, the question is, and you've been in academia, in our society, every incentive is to be very specialized and to really focus on one subject. And people don't talk and connect enough with each other. And I think we need that for AGI. What are you doing, or what can we do as a society to bring these 4 groups together? Is there conferences to exchange those 4 groups? How do you get these different people, these different tribes
Is that the short question?
Is that the short question?
Well, no. It was a long question. I hope he has a short answer, but...
Yeah, okay. Yeah, so Professor Friston's group's a neuroscience group. It's a theoretical neuroscience group. They have very strong mathematicians, very strong computer scientists. DeepMind's a bit of a case study in this. They get neuroscientists, computer science, sitting in the same room. So it's the very beginning, but I think that you need more. I think you need psychologists. Yeah, so we need a little bit more input from other science sectors to begin with, and ultimately you have to build these things. The theory is going to come from a very, very strong scientific, mathematically competent person, okay? You can get all the psychologists talking in a room and everybody else, but ultimately someone or a couple of people have to write down a scientific theory, just like Einstein wrote down the theory of relativity. So maybe I was a little bit generous. We need everybody. We need the ideas from everywhere, but the actual person himself or herself is going to have to be very super strong in math. We saw some of the math. It's not simple. It takes a while, right? Is a huge, just like the theory of general relativity, and I'll end here. We can understand the concepts, but the actual math is really, really, really hard, right? I don't know if you've ever tried it to solve the field equations. I have. They're not easy, right? Yeah. So don't expect this to be easy. It's going to be simple, but the math is still going to be, hard. Okay. Yeah. That was it. Okay. Thank you.
Okay, Peter. One more question. Where can we find your slides? Are you going to upload them somewhere?
Yeah, I thought the conference was going to upload them. If not, then my SlideShare, they're available on my SlideShare. So if you go to SlideShare and just Google Peter Morgan, I guess.
You'll find you?
You'll find him.
Okay.
I think that's the best way. And the other thing is just to look at Carl Friston. He has a great website with all his papers, which is super heavy going. But if you're really, really I don't know, if you really believe you want to try and solve intelligence, that's the best place to start.